So today, two of the three organizers have pressured the third into talking to us. So we have Sarah Peluse, who is going to speak to us about an asymptotic version of the prime power conjecture for perfect difference sets. So welcome, Sarah.
Thanks, Sean. So I've put the slides or a link to the slides in the chat if anyone wants to look at them while I'm speaking. So before I tell you about the prime power conjecture for perfect difference sets, let me first define what a perfect difference set is. So a perfect difference set is a subset of a cyclic group such that every non-zero element in that cyclic group can be written uniquely as the difference of two elements in the set. So for example, the set 1, 2, and 4 in the integers mod 7 is a perfect difference set. So these are some really rigid objects, and just for counting reasons, you can't find them in every group. So for such a perfect difference set to exist, we have to have that m is of the form n squared plus n plus 1, and that the size of D is of the form n plus 1 for some non-negative n. So in this situation, we'd say that the perfect difference set D has order n. So order is, in this situation, not the same as the size. And so this terminology mirrors the situation in, I guess, the study of finite projective planes. And the reason for that is that any perfect difference set gives rise to a projective plane. And if that perfect difference set is of order n, then the finite projective plane you get has order n as well. And you just take the points to be just the elements in your cyclic group and the lines to be all translates of your difference set. And then we assume that n is greater than or equal to 2, so that some axioms of projective planes are satisfied, and that every pair of distinct lines meets in exactly one point, and that any 2 points lie on a unique line in this projective plane just follows from the definition of a perfect difference set. So there are other projective planes besides the ones that you get from difference sets, but the ones that arise from this perfect difference set construction are known as cyclic projective planes. So we're interested in perfect difference sets because they're kind of examples of large Cdon sets. And Cdon sets are subsets of like a group such that there are no non-trivial solutions to the equation a plus b equals c plus d. And this connection to planes also shows that kind of perfect difference sets are object of interest in finite geometry, design theory, and also in coding theory. So lots of people care about these things. And the kind of most basic question you can ask about them is, when do they exist? So I said before that kind of the order of your cyclic group has to be of the form n squared plus n plus 1. But is that kind of the only restriction? So the question is, for which n do perfect difference sets of order n exist? And so it's been known for a long time that they exist whenever n is a prime power. And Singer constructed these examples. And it's an old conjecture that these are the only n that work. And the conjecture is known as the prime power conjecture. It says that a perfect difference set of order n exists if and only if n is a prime power. So what do we know about this? So it's been verified computationally for all n up to 2 billion. So it's a lot of good evidence there for it being true. And you can kind of more generally conjecture that all finite projective planes have prime power order, not just the cyclic ones. But as an example for how this is kind of a strictly more difficult conjecture, while we know that the prime power conjecture for perfect difference sets is true for all n up to 2 billion, we don't even know if there's a finite projective plane of order 12. So I'll just be talking about perfect difference sets today. So what's known kind of besides this computational evidence? So there's a lot of results about kind of specific perfect difference sets, but the most general ones that are in the literature are about possible orders of perfect difference sets that lie in some congruence classes. So there are results that eliminate all or almost all integers in some congruence class from possibly being the order of a perfect difference set. So maybe the most famous one is the result of Bruck and Reiser from 1949, which actually more generally holds for projective planes, that says that if n is the order of a perfect difference set and n is congruent to 1 or 2 mod 4, then n has to be the sum of 2 squares. And the sums of 2 squares have density like a constant times square root of log n in the integers. So this is a zero density set in these congruence classes. So there are also results that are specifically for perfect difference sets, and not just, or not all projective planes. So there's a congruence restriction of Jung-Napoleon and Vetter that gives, eliminates basically all the congruence classes mod 8, and also one of Wilbrink that eliminates congruence classes mod 9. And it's kind of a big open question in the theory of perfect difference sets, whether there exist kind of any congruence obstructions mod other prime powers. Yes, prime powers above 9. Kind of all of these results taken together, kind of combined, don't even show that the set of orders of perfect difference sets has density 0 in the integers. You just kind of remove a positive proportion. I guess a positive proportion less than 1 of the possible orders of perfect difference sets. So the result I'll be speaking about today says that yes, the set of orders of perfect difference sets has density 0 in the integers. And in fact, it has the order predicted by the prime power conjecture. So the number of orders of perfect difference sets below n is asymptotically n over log n, which is the number of prime powers below n. So I can actually get a explicit expression for this little of 1 term. It's this thing. So e to the minus some constant times 5 logs over 6 logs. And so this result, I guess, gives more evidence towards the truth of the prime power conjecture. But you might be wondering, can I say anything about the more general prime power conjecture for finite projective planes? And the answer is no, well, at least not yet. So kind of my proof uses a lot of results that are just for cyclic projective planes. And I don't know how to generalize this to more general projective planes. I'd be interested if anyone could. So before I start talking about the proof strategy, are there any questions about this or any of the previous slides? Okay, so if not, we'll keep going. Oh, I see Sean.
So the condition that your congruence conditions, did those apply to just perfect difference sets, or do they apply to all projective planes?
This result of Bruck and Reiser is for all projective planes, and these two are just for perfect difference sets. Any more questions? Okay, I'll keep going. So how do you prove something like this? So an important point is that I don't prove any new kind of structural theorems about perfect difference sets. Oh, this is spelled wrong. all that I use are a few kind of 70-year-old results about perfect difference sets. And these results kind of basically say that if n is the order of a perfect difference set, then there certain relations must hold between the prime factors of n and the prime factors of n squared plus n plus 1. So kind of bounding the number of orders of perfect difference sets then becomes a problem in analytic number theory. So you want to show that kind of these old results basically hold almost all of the time. So the first of these old results is Mann's theorem. It was proved in 1952. And it says that if n is the order of a perfect difference set and n is not a perfect square, then for any prime p dividing n and prime q dividing n squared plus n plus 1, p has to be a quadratic residue modulo q. So this is going to be a very useful result for us. It'll eliminate basically the majority of possible orders of perfect difference sets, but it's not quite enough. So it turns out to basically give us an empty condition when n squared plus n plus 1 is a prime that's congruent to 1 mod 4. So why is this? Well, if p is an odd prime, then, or if p dividing n is an odd prime, then n squared plus n plus 1 is 1 mod p, so it's definitely a quadratic residue. But then by quadratic reciprocity, this says that p is also quadratic residue modulo n squared plus n plus 1, since n squared plus n plus 1 is 1 mod 4. So then every prime dividing n is a quadratic residue mod n squared plus n plus 1, and just the conclusion of Mann's theorem trivially holds. Okay, so we're going to need something else. So why do we need something else? Well, just using Mann's theorem, we can get a big O bound on the number of possible orders of perfect difference sets, but we have to deal with the case when n squared plus n plus 1 is a prime that's 1 mod 4, because we expect this to happen by the Bateman-Horn conjecture at least a constant times n over log n of the time. Okay, so we don't know this. This is like a famous open problem, but we're going to have to deal with this case to get an actual asymptotic result. So I said I'm not going to prove any new real structural theorems about perfect difference sets, but I do have to prove a lemma. But this lemma is kind of a fairly easy thing to prove using the theory of multipliers of perfect difference sets. So the concept of multipliers is something that goes back to Hall in the 40s. And it's not too hard to show the following lemma, which says that if n squared plus n plus 1 is a prime that's 1 mod 4, and p is a prime dividing n, then p has to be a quartic residue modulo n squared plus n plus 1. And fortunately, this is not an empty condition, and it's not an empty condition for, say, like some congruence class of n modulo like 8. It turns out to be good enough for our purposes to show that the number of n such that n squared plus n plus 1 is a prime that's 1 mod 4, and n is sort of a perfect difference set, is little o of n over log n. So how do we use these results? So the results I just told you should kind of be enough to convince you heuristically that the number of non-prime power order perfect difference sets below n is little o of n over log n, because kind of for typical n or n squared plus n plus 1, one of these will have a large number of prime factors. And so the conditions of these two results should be really hard to satisfy. Like typically n or n squared plus n plus 1 will have like log n prime factors. And then we're flipping like log n or log n squared coins and hoping that they're all heads. And that's just not going to happen that often. But the problem with this heuristic is that obviously n and n squared plus n plus 1 are not just kind of independent random numbers of size big N and big N squared, because n squared plus n plus 1 obviously depends on n, and so do its prime factors. Okay, so the key idea to get around this is that the conditions imposed by these results I just stated are so strong that we can actually afford to lose some things, and we can use the union bound in some places to remove the dependence of some of the prime factors of n squared plus n plus 1 on some of the small prime factors of n. And once we do this, we've lost a little, but we've gained some independence, and the strength of Mann's theorem and the lemma are enough to kind of make up for the loss we got in the union bound. So this sounds kind of vague. So for the remainder of the talk, I'm going to talk about how I actually do this in practice. So how this is actually done kind of depends on the prime factorization of n squared plus n plus 1. So we have to split into 3 cases. So the first is that n squared plus n plus 1 has at least 3 prime factors. Second is that it has 2 prime factors. And the third is the only remaining case that it's prime. And kind of as the number of prime factors decreases, of course, the size of the set of n that we have to bound decreases. So if you just deal with the first case, well, that's enough to get big O of n over log n bound. And also, kind of as the number of prime factors decreases, and the difficulty of the argument increases. So I just said that. And so I'm going to go through first the case when n squared plus n plus 1 is 3 prime factors, or at least 3. So in this situation, clearly n squared plus n plus 1, since it has size at most like n squared, it must have a, or typically, or I guess it always has a prime factor below n to the 2/3. And typically, any little n below big N is divisible by at least 2 distinct primes below n to the, say, 1 over 100. And we also have to assume that they're not 3, kind of for technical reasons. And the contribution of the n that aren't typical, that don't have these 2 small prime factors, they can be bounded in a similar manner to what I'm about to sketch. So we start by splitting up these n, such that n squared plus n plus 1 is at least 3 prime factors, based on the primes p1 and p2 dividing them, and the prime q dividing n squared plus n plus 1. So here we've used the union bound, and we want to bound the size of these individual sets first, and then sum over the primes. So we apply Mann's theorem, and that just takes this condition that n is the order of a perfect difference set and translates it into these quadratic residue conditions. So if p prime is a prime dividing n, then p prime has to be a quadratic residue mod q, since q divides n squared plus n plus 1. And similarly, if q prime is a prime dividing n squared plus n plus 1, then p1 and p2 have to be quadratic residues modulo that prime. But fortunately, so bounding the size of each of these individual sets is a sieve problem of dimension 5/4, and kind of crucially, 5/4 is greater than 1. So that means that by applying an upper bound sieve, the size of each of these sets is like n over log n to the 5/4. And even though we lose some by summing over these primes, kind of this extra log n to the 1/4 saves us enough over the number of prime powers below n. So this is an example of what I mean by Mann's theorem being strong enough that we can afford to lose something by applying the union bound, because we gain a lot more back by using Mann's theorem and like an upper bound sieve. Okay, so why is bounding the size of this set, a sieve problem of dimension 5/4. Well, so this quadratic residue condition, so this removes half of the primes from possibly being able to divide n. So that removes 1/2 of a congruence class on average. And this condition removes kind of 3/4 of the possible q primes from being able to divide n squared plus n plus 1. And okay, so it's slightly more complicated here because not every prime can divide n squared plus n plus 1. But as long as p1 and p2 are not 3, then this condition and the condition that the prime actually divides n squared plus n plus 1 are independent. And if a prime divides n squared plus n plus 1 and it's not 3, then n squared plus n plus 1 actually has 2 roots modulo that prime. So in the end, this ends up kind of eliminating 3/4 of the a congruence class modulo each prime on average. So we have 1/2 from this plus 3/4 from this gives 5/4. So that's how we get, that's a sieve problem of dimension 5/4. So if we actually apply an upper bound sieve, in the end, we get that this thing we got from applying the union bound is bounded above by the same sum over primes of n divided by p1, p2, and q, and log n to the 5/4 as we expected, times some extra arithmetic thing from using the sieve. Because it's not quite true that exactly like 5/4 of the congruence classes are removed modulo every prime. That's not even a whole number. So this Euler product is basically some partial Euler products of some L functions multiplied together. And it's luckily pretty small on average. Like it's really easy to bound its moments. So in the end, we just lose some extra powers of log n, but we are already losing some logs by summing over these primes. So the contribution of n such that n squared plus n plus 1 has at least 3 prime factors is kind of easily admissible. So are there any questions about this before I talk about fewer primes? Okay. So when n squared plus n plus 1 is the product of 2 primes, things get more complicated. So let's assume that n squared plus n plus 1 is q1 times q2 with q1 smaller than q2. So then we need a different argument depending on the size of the smaller prime. So note that when the smaller prime is below n to the 2/3, this is just covered by the previous argument. Like all we used about n squared plus n plus 1 having at least 3 prime factors is that it had some prime factor below n to the 2/3. So when q1 is between there and n divided by some large power of log n, kind of variant of the previous argument also works. It's just a little bit more complicated. But when q1 is between n divided by this large power of log n and n divided by square root of log n, you really need a different argument. You still use Mann's theorem, but you have to argue kind of in a much more delicate manner. Like you really can't afford to lose anything. And finally, when q1 is really close to n, actually completely forget the anything about perfect difference sets and just show that the number of n below big N, such that n squared plus n plus 1 is the product of 2 primes that are very close together, is very small. And I do this using an enveloping sieve argument. So I'm not going to say much about this because either you know how these arguments go, and then kind of it's a pretty routine enveloping sieve argument, or you don't, and then I don't really have time to explain it in a way that's not like just confusing and full of like huge expressions that fill up an entire slide. But I will mention, so even though I said the enveloping sieve argument itself is pretty routine, it actually has a pretty interesting input. So to do it, I required a asymptotic for the count of certain points on this three-dimensional hyperboloid, where x, y, and z have to satisfy kind of various size and congruence restrictions. So I kind of enjoyed that. I wanted to say something about perfect difference sets, but then I had to count points on surfaces. So in the product of two primes case, I'm really only gonna talk about this third case when n squared plus n plus 1 has a kind of decently large, like smallest prime divisor. Also because similar ideas will come up when dealing with the case when n squared plus n plus 1 is a prime. Okay, so what do we do in this situation? So we start by splitting these n up based on their smallest prime factors. So their smallest k prime factors for k something like very slowly going to infinity. And we want these k prime factors to all be below log n. And kind of the number of n, such that n squared plus n plus 1 is the product of two primes. And also it doesn't have k prime factors below log n, turns out to be negligible. So it's fine to ignore them. And here, so this is kind of the, I guess, worst part of the argument quantitatively. This is where the 5 logs over 6 logs thing comes in. So this k is actually this quantity that's in the exponent of the little of one thing. So this is like some constant times 5 logs of n divided by 6 logs of n. So k is very small. So we break up n based on their smallest k prime factors, and also the prime factor of n squared plus n plus 1 that lies in this interval we're focusing on. And then we apply the union bound and Mann's theorem to reduce it to bounding the sum over all of these k tuples of primes, and then primes q in the interval we care about, such that each pi is a quadratic residue modulo q of the basically number of little n below big N that are, as you'd expect, that have p1 up to pk as their first k prime factors, have q dividing n squared plus n plus 1, and are the product of q and another prime. So here I've just applied the union bound and used Mann's theorem to say, well, we only need to sum over this, we only need to sum over primes that satisfy this quadratic residue condition. So kind of what all that really remains is to bound the size of these sets I call T. And we can do that using an upper bound sieve again. So we get kind of this slightly complicated looking quantity. But one thing I want to point out about it is, see, we save this log n here, and that's actually crucial. And that's why we can't push this argument all the way up to n. Like we have to stop at n divided by some power of log n that's below 1. Because if you go all the way up to n, you kind of don't gain anything by using an upper bound sieve to bound the size of these sets. Right, so we apply an upper bound sieve to get this complicated looking thing. And then the first thing we want to do is sum over the q's. So we really only have one thing depending on q here, and it's a 1 over q factor. And there are only 1 over 2 to the k times the total number of primes in this interval, possible choices of q to sum over. So we save a factor of 1 over 2 to the k here. And this is our savings of e to the negative some 5 logs over 6 logs thing. So summing over these q's saves us an n over log n, and then multiplies by a log n that cancels here. And that's how we get n over log n times something depending on k that gives us a savings. So we get log k over 2 to the k savings in the end for the number of n below big N, such that n squared plus n plus 1 is the product of 2 primes, with 1 the primes in this interval, and n is the order of a perfect difference set. Okay. So now I can finally talk about when n squared plus n plus 1 is a prime. So for the same reason that n squared plus n plus 1 being 1 mod 4 is a hard case, the case when it's 3 mod 4 is easy. So if p is an odd prime dividing n, then again, n squared plus n plus 1 is just 1 mod p. So it's definitely a quadratic residue. But then quadratic reciprocity says that the Legendre symbol of p over n squared plus n plus 1 is -1 to the p minus 1 over 2. So then Mann's theorem says that in this case, any prime p dividing n has to be 1 mod 4 for the consequence of the theorem to hold. So bounding the number of n such that n is the order of a perfect difference set and n squared plus n plus 1 is a prime that's 3 mod 4 is basically like bounding the number of n such that n squared plus n plus 1 is like a prime, and n is only divisible by primes that are 1 mod 4. And this is a sieve problem of dimension 3/2, because the condition that n squared plus n plus 1 is a prime removes 1 congruence class on average, and only being divisible by primes that are 1 mod 4 removes half a congruence class on average. So an upper bound sieve gives us a bound of n over log n to the 3/2 for this case. So now we've reached the hardest part of the argument, which I think takes up more than half of the actual bulk of the argument if you write it out. The case when n squared plus n plus 1 is a prime that's 1 mod 4. So this is all that's left. And we begin the argument in the same way we did for the product of 2 primes that are reasonably close together. So we split n up based on its smallest k prime factors for some k that goes to infinity really slowly. And then, so we're gonna have the size of some set to bound. So this is just n such that n squared plus n plus 1 is a prime that's 1 mod 4, and is the order of a perfect difference set, and p1 up to pk are the first k prime factors of n. So then we're gonna wanna bound the size of these individually and then sum up over p1 up to pk. So how do we bound the size of these sets I call T? So recall the lemma from earlier in the talk that says that if n squared plus n plus 1 is a prime that's 1 mod 4, and if p is a prime dividing n, then p has to be a quartic residue modulo n squared plus n plus 1. So this just says that each of p1 up to pk must be a quartic residue modulo n squared plus n plus 1 for each of the n in this set T. So how do we use this? Well, kind of one version of quartic reciprocity then says that for each of p1 up to pk to be quartic residues modulo n squared plus n plus 1, we have to be able to write n squared plus n plus 1 as the sum of 2 primes, or the sum of 2 squares, satisfying certain congruence restrictions modulo the primes p1 up to pk. Right, so we're basically counting the number of primes of special form that can be represented by this quadratic form with some congruence restrictions. And we can do this using the Selberg sieve. But one of the inputs we need for the Selberg sieve is an asymptotic count with pretty good error term of the number of points on this 3-dimensional hyperboloid with various size and congruence restrictions on x, y, and z. So now we have another lattice point count, and we prove this one and the one I mentioned earlier by adapting an old argument of Hooley. So you can probably get better bounds than what I actually get using like some automorphic form arguments, but it turns out like kind of this low-tech way is good enough for our purposes. Right, so then you use the Selberg sieve with this point count as an input to bound the size of the sets T, and then sum over the primes P1 up to Pk. And you actually end up having to do the same computation as for the product of two primes case that I showed you. Kind of what you get after bounding these using the Selberg sieve is the same thing as what you get after applying an upper bound sieve in the previous case and summing over the Q. So you get the same kind of savings of log K divided by 2 to the K in this case. So the error term coming from this situation and from the product of two primes that are relatively close together are essentially the same. Okay, so to review, so I've said a bit about how to cover all of the cases. So when n squared plus epsilon is 3, 2, or 1 prime factor, and needed to prove the asymptotic version of the prime power conjecture. And so what I've showed you is kind of what I proved, which is an upper bound. So we bounded the number of non-prime power orders of perfect difference sets. And then of course, Singer's construction gives the lower bound. And as I said, the largest contributions to this little of 1 error term come from n such that n squared plus n plus 1 is the product of two primes that are pretty close together, or n such that n squared plus n plus 1 is a prime that's 1 mod 4. And to finish, I want to say something about possible asymptotic versions of other difference set conjectures. So there are a ton of conjectures in design theory about the existence of kind of a bunch of different types of difference sets. So instead of perfect difference sets, which are such that every non-zero element of a cyclic group can be written uniquely as the difference of two elements, kind of more general difference sets ask for sets that such that every non-zero element can be written in exactly, let's say, like 5 ways as the difference of two elements in the set. You can make similar definitions in groups other than cyclic groups, abelian and non-abelian. And there seem to be a lot of conjectures that are important to people for a variety of reasons. So the one that's most interesting to me is the prime power conjecture. But I think the next most interesting one to me is what's called the circulant Hadamard matrix conjecture. So I'll tell you what a circulant Hadamard matrix is. So a circulant matrix is a square matrix in which every row is just a cyclic shift of the previous row. And a Hadamard matrix is a square matrix with plus or minus 1 entries whose rows are mutually orthogonal. So if it's an n by n matrix, then a Hadamard matrix times its transpose is just a matrix with n's on the diagonal and zeros everywhere else. And then a circulant Hadamard matrix is a matrix that is both a circulant matrix and a Hadamard matrix. And the conjecture is that these only exist of dimensions 1 by 1 or 4 by 4. And there are examples of ones that are 1 by 1 matrices and 4 by 4 matrices. So the connection to different sets is that the circulant Hadamard matrices are in 1-to-1 correspondence with what are called Hadamard difference sets in cyclic groups. So you can kind of just read off from the matrix what the elements of your set should be. And like these existence criteria I told you about for perfect difference sets, there are also some for Hadamard difference sets. But they are not nearly as easy to work with. So there are a few existence criterions, and they're either not strong enough to show some good bound on the possible number of circulant Hadamard matrices, or they're strong, like kind of conjecturally, but to actually use them to show that there are a few circulant Hadamard matrices, you really quickly run into some like extremely difficult problems in number theory, like having to show that there are like a huge number of non-Weifert primes. This is like an extremely difficult question related to the ABC conjecture. So I'd be really interested if someone could prove an asymptotic version of the circulant Hadamard matrix conjecture, because I currently don't know how to. Okay, I think I'll stop there.